Hi, welcome back. In this lecture, we're going to look at eigenvalues problems in computational electromagnetics. We're going to first formulate our eigenvalue problem, and then we're going to solve it numerically. There are typically two CEM applications. They can be either a driven system, where we seek the response to a source, for instance, an antenna emanating electromagnetic waves. So we inject a source, for instance, our electromagnetic waves, and then we calculated the response to this source. A second kind of problem is the so-called eigenvalues calculation, where we calculate the natural oscillation frequency of the system. In this kind of problem, we typically solve the non-zero field that satisfies the homogeneous problem, that is the problem without the sources. So this type of situation occurs typically for an electromagnetic system with a source that is non-zero for a finite time. So we calculate the response to a source that is non-zero for a finite time. So once the source vanishes, the field solution can be expressed as a superposition of eigenmodes, where each eigenmode oscillates at a particular eigenfrequency. So we're going to look at Maxwell equation in the frequency domain, like we saw in our recap of a Maxwell equation. In a linear dispersion-free medium, Maxwell equation can be written as a single second-order Curl equation for the electric field that is depicted here on the left part of this slide. So as we saw in the recap of Maxwell equation, we replace the Ampere's and Faraday law with a unique equation that is second-order equation that is also called curl because of the presence of these two curl operators. By expressing the electric field as a complex exponential, we can move from the time domain to the frequency domain. The frequency domain is here on the right side of my slide. So in the absence of the sources, so this term vanishes. And with harmonic dependence of exponential jt, where j is the imaginary number, the curl equation gives the following eigenvalue problem in the spectral space. So you see we have our operator, that is the curl operator, and then this omega is called eigenvalue of the problem. So the solution EM are the so-called eigenmodes. So what are eigenvalues and eigenfunction? As I saw in the previous slide, so for non-trivial solution where EM is different from zero, the omega m is called eigenvalue, and the corresponding E of m is called eigenfunction or eigenmode. If the region is a closed cavity with perfectly conducting boundary, that means that the tangential component of electric field around the boundary condition is zero. Then the operator on the right hand side, what we call actually L, this curl operator, is a self-adjoint. When an operator is self-adjoint, this expression is holding, right? So we have E1 and E2, where E1 and E2 are two eigenfunctions. And then we have an integral over a certain volume that describes somehow our inner product in the function space. So if this expression holds, the operator L, that is curl, is called self-adjoint. We can calculate analytically the eigenvalues as follow. There is derivation on the textbook. An important point I want to make is that when the operator is a self-adjoint, then eigenvalues are real and non-negative. So this is quite important. The eigenfrequencies are real for any lossless regions bounded by perfect conductors. The self-adjoint curl equation leads us to consider an eigenvalues problem of the type big L, where L is an operator acting on F equal to minus omega square of F. So this is our eigenvalue problem. And these need to be associated with a suitable boundary condition on A and 0. We assume that L is a linear self-adjoint operator with non-positive eigenvalue. So we know that if the operator is self-adjoint, then we support real non-positive eigenvalue. As a simple example to illustrate this general principle, we will study the 1D Helmholtz equation that is the following. So we have our independent variable x that is varying from 0 to a and associated boundary condition. So our f in 0 and f equal to a is equal to 0. And the Helmholtz equation is the following. So we have a second order derivative in f equal to minus k squared multiplied by f. We know how to solve this equation. In order for having non-zero solution for a eigenfunction or eigenmodes, the k must be, that is our eigenvalues, must be m multiplied by pi over a. So where m is an integer. So we will have a series of eigenvalues. In this plot, we have the first eigenfunction that are related to the first eigenvalues. So in the case, for instance, that we have a simulation box that is long pi, so here we will have this pi cancel out, and our eigenvalues will be all these integer numbers, so 1, 2, 3, and 4. So we want to solve numerically the Helmholtz equation, that is this eigenvalue problem. So we use the usual technique. So to discretize the 1D Helmholtz equation by finite difference, we divide the interval from 0 to a into n sub-interval of equal length, h equal to a divided by the number of points, number of the cells. As we saw, the simplest finite difference approximation is the one that using a center finite difference, that is actually the following. So this part is discretization of a second order equation, and then the second part that is just replacing the function with the values on the grid points of the function itself multiplied by k. So the boundary condition in this case are going to be 0 for both sides, so there is no reason to include as the f0 and fn, so the values of the function at the boundary, as unknowns on our problem. And we can also express our second order derivative as a matrix problem. So we can write the following equation as a linear system with n minus 1 multiplied by n minus 1 matrix A. So because of the stencil operator, we can express our matrix as a 3-diagonal matrix, where we have on the main diagonals minus 2, that is taking care of this term here, and then we have a plus 1 and plus 1 for the points in the finite difference that are related to the number of points, to the central point. So these side points are the one on the minor diagonal. So we have one here and one here. So our initial Helmholtz equation or eigenvalue problem can be expressed as A, that is this matrix, multiplied by F, that is the unknown terms of our values of a function f defined for each of the grid points. And then we have lambda, that is the eigenvalues and the function itself. So what we can do, there is a special function in MATLAB to calculate the eigenvalues given the matrix, this matrix A. So what we're going to do is to form this matrix A, and then we're going to provide this matrix A to the eigenvalue function to calculate the eigenvalues problem. The eigenvalues function is called Eig in this case. So one important point that I want to make is that this matrix A is largely dominated by 0, so there are several 0. So there are a nice way to express these matrices when there are many 0. These matrices are called sparse. So when there are many non-zero entries, we can use the so-called sparse representation of the matrix. So when n is large and A consists mostly of 0, and this can be exploited by saving the matrix in the so-called sparse form. In order to use this sparse format, we call the spalloc function to allocate this sparse matrix. The physical eigenvalues minus k squared are simply the eigenvalues of the matrix A. These eigenvalues can be easily computed with MATLAB routine Eig. which computes all the eigenvalues and corresponding eigenvectors of an algebraic eigenvalues problem. So let's look at a simple code to calculate the eigenvalues of a 1D Helmholtz equation using a finite difference. So the whole point of this exercise is actually to form the matrix A. So we saw that this matrix A is sparse and is composed by 3 diagonals. So we allocate our matrix in sparse formats using the sparloc function in MATLAB. Then we initialize the diagonal entries and then upper and lower sub-diagonals. So on the major diagonal we're going to have 2, but also we need to add minus 2 on the major diagonal, but also we need to take care of h squared. So here this is our term on the main diagonal. And then we are going to have 1 and 1 on the minor diagonals. So these are the function to calculate, to form our matrix. And then we can calculate the eigenvalues, in this case we call lambda, by calling the function eg of A. And then our k will be the square root of the minus lambda. So note here that also we want to sort the eigenvalues, so they will be in not sorted out. So we want to sort it from smaller to larger, so in increasing order. So we call this function to calculate the eigenvalues, basically giving 2 values. One is the size of the domain, where we want to calculate our eigenvalues, and then it is the number of grid point. So the number of sub-interval, that means the number of cell. So if we call this function where a is equal to pi, so we go from 0 to pi, and then we use n cell, we got this series of eigenvalues. So as you can see, the values are quite close at the beginning to integer numbers. So we have 0, 99, and then 196 and 2.89. So we saw that with the increasing order, the eigenvalues are not getting better and better. Actually, the accuracy decrease quite a lot, only for the small one. So what we can do is to increase the number of grid points, and we see that we get a better and better approximation. Still some issues for the larger eigenvalues. So what we can do is to increase the number of cells to increase the accuracy of our eigenvalues calculation. So we can perform convergence test, and we will find that the convergence is also of second order accurate. So this was the first lecture on eigenvalues calculation by calculating the eigenvalues in the spectral domain. In the next lecture we are still using the finite difference to calculate the eigenvalues, but we will be in the time domain. So we will solve Maxwell equation in the time domain, and then we will apply spectral analysis to do exactly the same job that we did in this lecture. Talk to you soon.